Okay, so let's change gears here, and we're going to get into conductor clearance questions before we move on to overcurrent protection and ampacity. What is the lowest point you can attach the overhead service conductors to a structure? So we've got some options here, but the first thing we do is we pick apart our question, and we're going to use the index and the keyword process. We're dealing with overhead service conductors, so let's flip to O in our index and see if there is even a section called overhead service conductors. If not, we'll kind of switch gears, but first always start with the most obvious. You're dealing with overhead service conductors, so let's start there. Okay, so we look at the black bold headings until we find overhead service conductors. It has its own section. Under that heading, we're going to continue to look for keywords in the question. As we look down, we find point of attachment. If you notice up in our question, what they were asking was the point it can be attached. So under our subsections, we're looking for something, similar in our question. We find point of attachment. It refers us to two articles, 230.26 and 230.28. So we need to keep our finger in the back of the index just in case we need to flip back. We read that in 230.26 it cannot be lower than 10 feet. Okay, so what is the minimum clearance height for a 120/240 service conductors coming from the utility pole to a service attachment point that passes over areas or sidewalks accessible only to pedestrians? So let's pick apart the question, use our index process and our keyword process. We're dealing with overhead service conductors, so we're going to flip to O in the index. Okay, so we find under overhead conductors, under the subsection, we find clearances. 230.24 is the first article of 3 that it references, so hold your place in the index. Go ahead and flip to 230.24 now. It's on page 85. Now that we feel like we're in the right section, we're going to use and look at the black bold headings until we find what we're looking for. So we look at part A, and it is dealing with roofs and going above the roof. But if we look at part B, it's dealing with vertical clearances. And when we read section 1, we find exactly what we're looking for. It says 10 feet, but we need to read through that whole section and make sure it's what we need. It's looking for electrical entrances above sidewalks accessible only to pedestrians, measured from final grade. So this is exactly what we need. And it's the voltages do not exceed 150 volts to ground. So we're good there because we have 120 to ground, but 240 only across the two phases. So section 1 is what we need to select from, and we select 10 foot. Okay, what size AWG aluminum conductor and protection would you select for a service with a total calculated load of 47,000 VAs and a single family dwelling on a 120/240 volt system? So it's going to be the same process. We're just dealing with aluminum conductors, so we'll use the right hand side of 310/15B16. So first we need to find out how many amps that we're dealing with, and then select our overcurrent protection. So we just use our Ohm's law, and we know our power and our voltage, and we need to find our current. So we'll divide 47,000 divided by 240. That equals 195 amps. We're going to go to our standard breaker chart of 240.6A, and we're going to choose the next size up, which is 200 amps. Okay, so now let's size our wire. We're dealing with a 195 amp load, and if the code book were simple, we could jump to our ampacity tab and size the wire to 250 kc mils and move on with life. But it's not, so we have to apply 310 1015B7 on page 149. So if the service protection is 1 to 400 amps, a 0.83 reduction factor can be applied, then size the wire. So we're dealing with a 200 amp breaker. So we must take 200, multiply it by 0.83. That's going to give us 166 amps. Now this is our new load that we size our wire by. So we head back to 31015B16. We find that in the 75 degree column that 4/0 aluminum is good for 180 amps. So we select 4/0 on a 200 amp overcurrent device. What is the temperature correction factor for a USE2 number 6 copper conductor with an ambient temperature of 51 degrees C? Okay, so the first thing we do is check and make sure USE number 2 is in our 90 degrees C column of our ampacity chart. So we look under these initials. Sure enough, I see USE number 2. So we're good to proceed. Now let's flip over to our temperature adjustment factor table. We go to 310.15B2A and we look for our new ambient temperature. This time we're going to be on the left side of the table because we're dealing with Celsius. So we look for where 51 degrees falls. We find that in between 51 and 55. And then we have to slide over to the 90 degree C column, and we're going to find that the correction factor is 0.76. So we select C. What is the allowable ampacity of a THHW number 6 conductor with an ambient temperature of 142 degrees terminating to 75 degree terminals? So the first thing we do is check and make sure that THHW is in our 90 degree C column. I'm going to flip over and we look and we find THHW, so we can proceed in the 90 degree C column. It is there, so now we need to see how many amps that the number 6 is good for at the 90 degree chart. So we look, we're in the 90 degree chart, we're looking at number 6, and we find that number 6 is good for 75 amps. So now we head to 310.15B2, which is our ambient temperature correction table, and we're going to search for our new temperature of 142 degrees. And it falls down in between the 140 and 149. We find that our correction factor is 0.65. So we just multiply 75 amps multiplied by 0.65. Our new allowable ampacity for this wire is 48.75. So we select B. What size copper THHN conductor would you select for a 49 amp load in an area with an ambient temperature of 110 degrees terminating to 75 degrees C terminals? First, we go to our ampacity chart and we make sure that THHN is in the 90 degree column. It is, so we can select from there to do our adjustments. Now we need to figure out what conductors will cover the amp load as of right now. So you just have to find somewhere to start. First, select a conductor that can carry the 49 amps before the adjustment factors. we find that on the 90° C chart, that number 8 wire is good for 55 amps. So that will handle our load as is before we apply any correction factors. So let's carry on. Okay, so we head to our temperature adjustment table and we search for our new ambient temperature of 110 degrees. At our temperature chart, we find that our correction factor is 0.87 for 110 degrees Fahrenheit. So we take our 55 amps, we multiply it by 0.87, and we get 47.85 amps. Now that we made our correction factor, will 47.85 cover our 49 amp load? No. So we must try the next size up wire and see if it will cover our 49 amp load after the adjustment factors. So number 6 is good for 75 at the 90° C column. So we take 75 and we multiply it by 0.87 and we're going to get 65.25, so we're good to go. That will cover our 49 amp load. So we select C, number 6. What size copper THHN conductors would you select for a 49 amp load in an area with the ambient temperature of 43° C terminating to 75° C terminals? First, we go to our ampacity table and see if THHN is in the 90° column. It is, so now we select a conductor that will cover the amp load as of right now. So number 8, 55 amps, would cover the load before we apply the correction factors. Okay, so we head to our temperature adjustment table and we search for our new ambient temperature of 43° C. So we're going to be on the left-hand side of this table. At our temperature chart, we find a correction factor of 0.87 at 43° C. So we multiply our original amperage, which was 55, by the correction factor of 0.87. We're going to get an allowable ampacity of 47.85. Now will 47.85 cover our 49 amp load? No, so we must try the next size up. Number 6 is good for 75 amps at 90° C. So we apply the correction factor just to make sure we're good. So you take 75 amps, you multiply it by 0.87, and you're going to get 65.25, so we're good to go. What size feeder conductors would you select for a 100 amp overcurrent device for a feeder that is servicing one apartment unit using copper conductors on 75° terminals? First, we flip to our ampacity tab in our code book. We're dealing with a feeder for a single unit, so we must use 310.15B7. So we're going to take 100 amps and we're going to multiply it by 0.83. And that's going to give us 83 amps. Now we go size our wire based on our new allowable load. And that is going to give us, from our 75° column, we see a number 4 that is good for 85 amps. What size feeder conductors would you select for a 100 amp overcurrent device for a feeder that is servicing one apartment using aluminum conductors on 75° terminals? First, we flip to our ampacity tab in our code book. We're dealing with a feeder for a single unit, so we must use 310.15B7. So we take 100 and we multiply it by 0.83. That's going to give us 83 amps. In our 75° column for aluminum, we see that number 2 is good for 90 amps. and we select B. Let's jump right into it. What size copper conductors would you select for a 7.5 horsepower, 208 volt AC 3-phase motor terminating to 60° C terminals with a nameplate FLA rating of 26 amps? We never size regular motor conductors from the nameplate rating or the FLA rating. If the FLC is printed on the nameplate, we can use it. First thing we want to do is go find what our FLC is for this motor. Let's head to our motor FLC tables using our FLC tab. This time we're going to make sure that we're going to go to our three-phase table. So we're going to go to 430.250. So what is our FLC? First we look at our horsepower on the left-hand side, and then we slide over, find our what voltage column we're in, and then we select our amperage. Okay, so our FLC is 24.2 amps. The question offers no special information, so we just multiply it by 125%. So we take 24.2 and we multiply it by 1.25, and we get 30.25. Now we size our conductors and head to our ampacity table. We can drop the 0.25 and just use 30 amps. So what wire size should we use from the 60° C column? So you head to 310.15B16. You head to your 60° column. What wire should we use? We're going to use C. We're going to use 10 gauge wire. What size copper conductors would you select for 5 motors with FLCs of 24 amps, 13 amps, 13 amps, 10 amps, and 9 amps, terminating to 60° C terminals? Everyone head to 430.24 and let's highlight it. And let's go ahead and read it. Okay, for several motors, or motors and other loads, conductors supplying several motors or motors and other loads shall have an ampacity of not less than the sum of each of the following. So 1 is 125% of the full load current rating of the highest rated motor. Number 2 is the sum of the full load current ratings of all other motors in the group as determined by the way that we've been doing it. And then if you ever got into these type questions, and I don't think you would, but if you had other loads, you would do 100% of the non-continuous motor load and 125% of the continuous non-motor load. So what it's saying is you take the largest motor, go ahead and multiply it by the 1.25, and then you total up all the other motors together and treat it as one new motor. And then you're going to add those two numbers back together, and that is going to be your load for your ampacity for sizing your conductors. Now we're going to go through how to do this. Okay, so what size conductors? Let's go through it. Our largest motor is 24 amps. So we multiply 24 by 1.25 and get 30 amps. Then we total all the other motors together and treat it as one new motor. That's just the way that I was taught to do it. You can just say that you're totaling them at all, however you want to do it. So you take 13 plus 13 plus 10 plus 9, and that is going to give you 45 amps. Now you just add it back together with the one that you did the multiplier to, and that is going to give us 75 amps. And now that is our overall load that we're going to size our wire by. So now we head to 310.15b16, our ampacity table, and we use the 60 degree C column because that's what our question specifies. And what wire is good for 75 amps at 60 degrees C? It's going to be number 3, D. What size copper conductors would you select for 4 motors with FLCs of 22 amps, 20 amps, 14 amps, and 10 amps terminating to 75 degrees C terminals? So we take our largest motor and do the 125%. So we take 22 and multiply it by 1.25, and that equals 27.5. Now we add them together and take 20 plus 14 plus 10, and that equals 44. Now we just take 27.5, add it back to the 44. We're going to get 71.5. Now we head to our ampacity table to size our wire. So what wire is good for 71 amps in the 75 degrees C column? It's going to be a number 4. Okay, what size copper conductors would you select for a single-phase motor with a nameplate rating of 26 amps that will run a drawbridge for only 5 minutes at a time, terminating to 60 degrees C lugs? So everyone head to 430.22e. These are the provisions in the code book for when motors will only run for fixed or limited amount of times. Let's go ahead and read it together. And it says, for other than continuous duty, conductors for a motor used in short time, intermittent, periodic, or varying duty applications shall have an ampacity not less than the percentage of the motor nameplate current that is shown in 430.22e. So if you look on the next page, on page 303, there's a table there. It's called duty cycle services. So, duty cycle service. I want you to go ahead and highlight that table. You're going to be using this table likely in your test. Okay, so if you look on the left-hand side of this table, it's describing different types of motors. The first one is short time duty operating valve and a few others. The second one is intermittent duty, freight and passenger, elevators, tool heads, pumps, and we see drawbridges, and that's actually in our question. So if you look here, first on the left-hand column, you select what type of motor your question's asking for. Then if you look across the top, it says for how long it's going to be running. So first you find your motor on your left, you find how long the question specifies, and then you go down and you find your demand factor. In this case, our demand factor is going to be 0.85 because in the second large column down, we're looking at drawbridges. We go over for a 5-minute rated motor, and the demand factor is actually going to be in your favor, and it's going to be decreased, allowing you to decrease the amperage and then size your wire. Okay, so let's take a look at our table and just kind of recap. We're looking at 430.22e. So we find what type of motor it is. In this case, it's a drawbridge, and then we slide over to our time limit. In this case, it is 5 minutes. Then we multiply our amperage by the demand factor. I do want to note that when you're dealing with duty cycle motors, in this case, for some reason, the code book allows you to use the nameplate rating instead of the FLC. So you're allowed to use the nameplate rating or the FLA, whatever one it lists, instead of the horsepower rating. I don't know why instead of the FLC, which would be determined by the horsepower rating. I don't know why the code book switches back and forth, but it does. If you're ever confused on something when you're taking your test, and you know you're in the right code article, read the code how it states it and just take it at face value. If it says do the FLC, do the FLC. If it says do the nameplate rating, do the nameplate rating. If you're ever confused anywhere in the code book, just read it exactly like it says it, because that's likely the way whatever question you're facing is going to answer it exactly how the code book says it. So our demand factor in this case is 85%. So we take our nameplate rating, which is 26 amps. We multiply it by our demand factor, which is 0.85. Now we get 22.1 amps. That is our new load. Now we head to our ampacity table, and what size wire can hold 22.1 amps at 60 degrees C? And we select 10 gauge wire. What size service conductors would you select for a 125 amp overcurrent device and a 119 amp load using aluminum conductors on 75 degree terminal lugs on a commercial building? First, we flip to our ampacity tab in our code book. We're dealing with a commercial building, so 310.15b7 does not apply. That's the 0.83 rule. So we must size the wire based on the load and make sure that the overcurrent protection device protects it accordingly. So we apply what we already know. We know that we go to the 75 degree column for aluminum, and we see that 1/0 is good for 120 amps. So we select D. What size copper conductors would you select for a 3-phase motor with a nameplate rating of 40 amps running on some short time duty operating valves that will run for only 15-minute intervals terminating to 75 degree C lugs? First, we find what our demand factor is in our duty cycle table. It's in table 430.22e. We go over to the left-hand side and find that we're dealing with short time duty operating valves. And then we slide over to our respective time interval, which is going to be 15 minutes in this case. And we find that our demand factor is 120%. So we multiply 40 by 1.20. That is going to give us 48 amps. Now we head to our ampacity table to size our wire. What wire can hold 48 amps in the 75 degree C column? And the answer is D. Okay, what section of the code book would you find the rules for sizing motor short circuit and ground fault protection? Let's use our index and our keyword processes. So what should we search for first? I say we go for motors. And then what keywords should we continue with? I say we do short circuit ground fault protection. So what section is it in? It's in 430.iv. Now we're going to flip to page 4 of our code book, and we're going to find out what page that's on. Anytime it tells you a section like that, you do not have to go through 430 and be looking for IV. You will just go to the front of your code book to the table of contents, and you will search for chapter 4. Then you'll look for 430. Then you'll look for 430 IV, and you'll flip to that page. In this case, it tells us to flip to page 307, and we're going to find part IV of section 430. And we're not going to read this whole thing together right now, but we'll be reading it a little bit at a time as we need it over the next few questions. What size AWG aluminum conductor and protection would you select for a service with a total calculated load of 52,000 VAs for a single-family dwelling on a 120/240 volt system? First, we need to find out how many amps we're dealing with and select our overcurrent protection. We just divide 52,000 by our system voltage, which is 240, and you get 216.66 amps. Now we use our standard size breaker chart, and we get a 240.6A, and we get the next standard breaker of 225. We're dealing with a 216 amp load, and if the code book were simple, we could jump straight to our ampacity tab, size the wire to 300 kc mils, and move on with our life. But it's not, so we have to apply 310.15B7 on page 149. So if the service protection is in between 100 and 400 amps, a 0.83 reduction factor can be applied and then size the wire. So we're dealing with a 225 amp breaker, so we must take 225, multiply it by 0.83. That's going to give us 186.75. We'll round up to 187. Now this is our new load that we size our wire by. So we head back to 310.15B16. We find that in the 75 degree column, that 250 kc mil aluminum is good for 205 amps. So we select 250 kc mil on a 225 amp breaker. What is the allowable ampacity of a 1/0 XHHW copper conductor with 13 current carrying conductors in a piece of 2-inch RMC? First thing we need to do is see if our conductors are listed in the 90 degree C column. We look up and we find XHHW, so we can select from that column before we do our adjustments. So first we find out what 1/0 is good before our adjustments. So we look in the 90 degree C column until we get down to the 1/0 selection. And 1/0 copper is good for 170 amps in the 90 degree C column. So it gives us the number of current carrying conductors, so we can head straight to our adjustment table. We find that our conductors falls in the 10 to 20 range because we're dealing with 13. And we slide over, and that is going to be a 50% adjustment factor. So we take our 170 amps and we multiply it by 0.50. That is going to give us 85 amps. So we select B. What size short circuit ground fault protection would you select for a 5 horsepower 208 AC 3-phase motor terminating to 60 degree C terminals with a nameplate FLA rating of 26 amps using an inverse time breaker? So there's a lot of information here. Some of it we don't need, some of it we do. We never size normal short circuit ground fault protection from the nameplate or FLA rating. If the FLC is printed on the nameplate, we can use it. So the first thing we do is we find what our FLC is. And we flip to our FLC tab. Okay, so we find in table 430.250 that our FLC is 16.7 amps. And now we're going to head to this new table I'm going to teach you about, and that is 430.52. And it's going to be on page 308. So flip over to page 308. You're going to want to highlight this table. It's going to be a table you're going to be using a lot. What we're sizing right now is a breaker or a fuse for this motor that is going to allow the inrush current as the motor gets started. And this device at the breaker or fuse is going to be designed only to protect if there's a short circuit or a ground fault. Next week, we're going to learn how to size overload protection. A motor over a certain horsepower is required to have both. You would have a breaker back at the panel that is going to protect it if it short circuits or ground faults, but then closer to the motor, sometimes built into the motor, you're going to have the overload protection, and that's going to protect it from getting too much load on it. It would shut the circuit off, and it would protect the motor from burning up and protect the conductors. But this week we're going to learn about sizing the overcurrent protection that is for short circuit and ground faults. So I want to kind of lay this table out for you. On the left hand side, it's going to be the type motor that you're using. And then if you look across the top, it lists the different types of devices. So the non-time delay fuse, the dual element, the instantaneous trip, and the inverse timer. So depending on what your question's asking for, in this case it's a polyphase motor, three-phase motor. So we select that column, and then we're going to slide over to the what type device it's using. In this case it's an inverse time breaker, and we're going to find that our multiplier is 250%. And we're going to learn how that applies here in just a moment. Okay, so we took, first we found our FLC, and then we went and we found the motor in the motor column that applies to us. Then we slide over to the type of device that applies to us and find our multiplier. Then we just do the math. So we multiply the FLC by 2.50, and that is going to give us 41.75 amps. Okay, so we did our math. Now, do they make a 41.75 amp breaker? Let's all read 430.52C1 on page 307, and we're going to be reading exception 1. The question is, they don't make a 41.75 amp breaker, but are we allowed to use the next size up rule when selecting this device, or do we have to go down and use the next size down? We're going to learn right here. So in 430.52C1 on page 307, in exception 1, it says where the values for branch circuit, short circuit, and ground fault protected devices determined by table 430.52 do not correspond with the standard size ratings or fuses, then the next size up and the next higher standard ampere rating shall be permitted. So you can do it in this case. I'm going to give you a little inside info. Next week we're going to size overload protection. You must use the next size down breaker. The next size up does not apply for overload protection, but we're going to cross that bridge next week. This week we're allowed to use the next size up rule. So we are going to go back over to 240.6, which is our standard ampere rating chart for overcurrent devices. If you close your code book, you can use your OCPD tab to take you to section article 240. And we're going to flip over to table 240.6a on page 95. And we're going to select the next size up. So what's the next size up standard ampere rating past 40? Looks like it's 45. What is the allowable ampacity of a number 6 THHN aluminum conductor with 6 current carrying conductors and a piece of 3/4 RMC? First, we see if our conductors are listed in the 90° C column. We're using aluminum, so we're going to use the right-hand side of table 310-15B16. Okay, we look over there, and our THHN conductors are listed. So first we find out what number 6 aluminum is good for before adjustments. So if you look in the 90° C column of the aluminum side of the chart, number 6 is good for 55 amps. So it gives us the number of current carrying conductors in our question, so we can head straight to our adjustment table. On page 148, we find that our number of conductors falls in the 4 to 6 column, so we slide over and we select 80%. So we take our amps, 55 multiplied by 0.80, it's going to give us 44 amps. So we select C. What size short circuit ground fault protection would you select for a 7.5 horsepower, 120 volt AC single phase motor terminating to 75° C terminals with an FLA rating of 71 amps using a dual element fuse? So we never size normal short circuit ground fault protection from the nameplate or the FLA. They're throwing that in to trick you into this question. If the FLC is printed on the nameplate, you can use it. You may have a graphic in your test that shows FLC, FLA on the nameplate. That's perfectly fine. As long as you're using the FLC, that's okay. First thing we want to do is find out what our FLC is. So we head to our FLC table using our FLC tab. In this case, we're dealing with single phase, so we're going to go to 430.248. We find that our FLC for a 7.5 horsepower, 120 volt, single phase motor is going to be 80 amps. So we head to table 430.52 to find out our multiplier. We find what type of motor it is on the left. We're dealing with single phase. And then we're going to slide over to the proper device, which is going to be a dual element fuse. And we find that 175% for dual element fuses. So that's our multiplier. So now we just take our FLC, we multiply it by 1.75. That's going to give us 140 amps. Now we just head over to 240.6A and we select the next size up. And if we look, we're going to find 140. And which one's the next size up? Looks like it's going to be 150. Okay, so how many cubic inches would you calculate for 5 number 12 AWG wires and 3 number 10 wires for box fill calculation purposes? So it's asking what's the total cubic inches of that many conductors. So first we head to table 314.16b. We find that number 12 is 2.25 per conductor and number 10 is 2.50 per conductor. So we just multiply. We have 5 number 12s multiplied by 2.25, and that is going to give us 11.25 cubic inches. Then we do 3 number 10s at 2.50. That is going to give us 7.5 cubic inches. We just add those two together, and that is going to give us 18.75 cubic inches. And we select B. What size round box would you select for 9 number 12 conductors? So we have some selections and we have D, let's wing it. And I have a feeling that most people out in the field, if they had a choice, it would be D, let's wing it until the inspector tells us we can't do it. I want you guys to be better than that. Anybody can wing it and pull wire. Be an electrician. Be an excellent electrician and become a licensed electrician. So let's all look at table 314.16a. It's one of my favorite tables. So we look there, we go over to the left-hand side and we find our box. The round boxes are up at the top. And then we slide over and we find the size wire that we're working with. And then we slide down and we find the box that fits our total conductors. So we have 9 in this case. It happens to be right on 9. You find your box, you slide over, and you see which box would we select? We would select the 4 by 2 and an 8 that fits, in this case, exactly 9 number 12s. How many number 14 conductors can you fit in a 4 by 1.5 inch square device box? Let's all look at table 314.16a. We're going to select what type of box that we're working with. Then we're going to slide over to the type of conductor. How many can we fit in there? You can fit 10 number 14 conductors in that size box.